Hello everyone, welcome to this online course on material science. This is lecture 21 in module 1 on magnetism. And if you recall, in the last lecture I have mentioned that the magnetic moment due to the orbital angular momentum, right, the L subscript for orbital angular momentum, is given by minus the g factor of the orbital angular momentum, and then the Bohr magneton divided by h bar times the operator itself, right? And then similarly for spin angular momentum, the magnetic moment due to spin angular momentum was given by minus the g factor of the spin times the mu b by h times the spin operator, right? And we have shown that the total magnetic moment, which is nothing but mu L plus mu S, right, and is given by minus mu B by H L plus twice S, right? So these are our expression from the last lecture, and our question is that if you look in these three expressions, these two moments are expressed as some g factor times mu bh times the corresponding angular momentum, right? But here you see the total moment is here is expressed in terms of these two angular momentum L and then twice S, right? So the question I was asked that can we represent this total angular momentum operator, right? So everything here are operators. So let me put the hats for consistency. So can we write this mu with this structure, where we will say on the right hand side we have minus sign some g factor corresponding to total angular momentum, then our mu b by h factor times only j, right? So here we have L plus twice S, but we want to express the moment in terms of this form, right? And the question is, this j factor, what's this value? And I have mentioned that usually this g factor is known as the Landau g factor, right? The Landau g factor. And the plan in this lecture is to show you how you can find out the value of this Landau g factor, right? And to do that, this g factor, let me start from the total magnetic moment expression, which is our plan is to write in terms of these g factors and then this mu b by h ratio times the total angular momentum, right? And we have seen that this total mu is nothing but mu b by h L plus twice S, right? And on the right hand side we have the same expression, g times j. So from this you can see these numbers or these values get cancelled. We are left with L plus twice S, which are vector operators. So let me put the hats, which is g times j. So we are trying to add twice of the spin operator with the angular orbital part, and this should be equal to some g factor times the total angular momentum, right? And from this expression we want to find out what is the value of g. And the question is, you always remember that, right, that this is an operator expression, right? And g is a number, L, S, j are the operators, right? You know that. So the question is, how do you find the number from the operator, right? For that, the trick is, first, let's define. So let's say we define some unit vector, right? Because these are all our vectors, right? So they're operated by vector operator. So define unit vector along j. So along this j vector, we will define some unit vector. Let's say the unit vector is denoted by n, and j, I'm saying that the unit vector is along j, right? And how do you define the unit vector? It's always the vector itself first divided by its magnitude, right? And we know that's an operator. So that's your unit vector. So our plan is here is that to take a projection on this unit vector, right, on the direction of j. So if somebody is telling you that let's take a projection of this expression along the vector j, all you need to do is to make a dot product with this expression with the unit vector, right? That's what the projection is all about. If you remember from your vector algebra that unit vectors, if you take some dot product with that vector, it's just the component along that vector, right? So we want to perform this operation. So L plus 2i's dotted with the unit vector, and then on the right hand side j times nj, right? So on both sides we are taking the dot product with the unit vector along j. And if you look on the right hand side and the left hand side, so let me evaluate the right hand side first because it's easier. So we have g, j, nj, right? So g, then we have the unit vectors. And what is this unit vector? It's the vector itself by its magnitude, right? So and that's j square, right? So on top we have the j squared operator, which I have mentioned in the last lecture, and on the denominator we have the magnitude of this vector. That's our right hand side. And what about this left hand side? You will see if you put nj is equal to the vector j divided by its magnitude. So the left hand side is nothing but L plus 2i's, all of them are vector operators, times j by the magnitude itself, right, of the j vector itself. And that's your right hand side, that's your left hand side. You can see these two gets cancelled from the both sides. So we have the expression L 2i's j is equal to jg square, right? So let me write out the full expression. First the left hand side, L plus 2i's, right? And then we dot it with the vector j. And on the right hand side we have g j square operator, right? Now the question is, on the left hand side you have the operator, on the right hand side you have a number times an operator, right? So how do you get a number from these operators? The idea is you always, I have mentioned this before many times, that to find the value from an operator you perform the expectation value. That's the rule, right? So you say that take the expectation value in both sides. Take expectation value in both sides of the operator of the equation, right? Both sides. So how do you represent the expectation value of some operators? You put an angular bracket. You remember all these things, right? I have discussed and I mentioned that this concept will become very handy, and now you can see we are using them frequently to understand our topic of discussions. So that's your angular bracket and expectation value on the left, and we have the expectation value. G is just a number, so that's outside the expectation value, and we need to find the expectation value of j square, right? So in this notation it's not really clear that okay, that's an expectation value, but the question you should ask that what is that state, right? I have always mentioned that to find the expectation value you need to know the operator and also the state on which you want to find out the expectation value, right? So here in this form we know that's the expectation value, but we are not yet we haven't specified what is the state, right? So let's specify the state here. Which state we are trying to calculate the expectation value. The state is labeled by 4 quantum number L. You remember what is L, right? Then S, then I would say Mj and J. So Mj and J. That's our state. And we remember what is Mj, right? Mj is nothing but Ms plus Ml, right? From previous lectures. And J can have two values, which is L plus L, S, and L minus S, right? These are the two values that J can have, and Mj is Ms plus Ml. And L and S are quantum numbers for orbital angular momentum. This is for the spin angular momentum. This is the J component, quantum number for the Jth component of the total angular momentum J, and this is the angular momentum of the total angular momentum J, right? So you know these things from the previous lectures. Now the question is, we need to find the expectation value in this state, right? So let me first evaluate what is on the right hand side. So on the right hand side we have G times J square. So now we need to write it out in the full form. The expectation value is always between a bra and a ket, right? And here in the middle we put the operator. And what will be the bra corresponding to this ket? But remember, usually we write the J first and then Mj, right? Maybe I should correct it here. That's more usual convention, that first you write L, then you write S, then J, and then Mj. And similarly for the ket, we have L, S, sorry, J, and then Mj, right? The 4 numbers. And you remember what J square acts on, right? And produces when they act on this state, because J square will talk to J and Mj, this two quantum numbers, right? And what it will produce, if you recall from the last lecture, that J square will produce the quantum number, the eigenvalue J times J plus 1 H square, right? That's the eigenvalue times the state itself. So the state remains the same, Ls J Mj. That's just a number. You can bring it outside the expectation value, right? The same rule that we have been using for a while. So G, and then we have J plus 1 H square, H bar square. And what we have two state, right? The inner product of these two state, L, S, J, Mj. And here we have L, S, J, Mj, right? And you know, orthonormality ensures this inner product has to be 1. So the value is, on the right hand side, we have J plus 1 H square, right? That's the value of the right hand side of this equation, which is this one. And we need to find out what is the expectation value of this operator on the left hand side, right? So let's copy what we have in the left hand side of this equation. We have L plus twice S, right, times J, an expectation value. We need to perform some manipulation in this part of the expression. Let me show you how to do that. The first thing is that you note that let's write the operator first, right? So in this expression, the operator part, let me just write the operator. Here is that L plus twice S, right? And dot with J. What is J? J is L plus S. It's the sum of this spin and orbital angular momentum, right? You know that from the previous lecture. And if you perform the dot product, right, you will get L dot L, which is L square. So first we will have L square, then we have L dot with S, right? So L dotted with S. Nice. Then we have 2 times S dot L, right? Let me write down them as they are ordered in this expression. Then we have 2 S square, right? s2s dot s is 2s square. Now the question is L dot s, and here we have s dot L. So you remember the problem of commutation, right? I have mentioned that operators can be exchanged in order if they don't, if they commute with each other. So the question here is to ask is that, does L and S commute with each other? Let me give you the rule here, is that the L and S, they commute with each other, right? That's the rule to remember for this derivation. So S dot L is same as L dot S. So that's that, then you can add them. So it's like 3 L times S, right? So on the right hand side we have, sorry, L square times 3 L dot S, because the order doesn't matter because they commute with each other, and plus 2s square, right? That's the expression for this operator. Now what is this L dot S? We need to understand this bit to find out the expectation value. So let's focus on this part of the expression. What is this L dot S? Now the L dot S, we need to find out this expression. For that, let's start what is J, right? If I don't put the hats, it should be okay with you by this time because we know that they are operators. But anyway, for consistency, I will try to put all the hats. So J is equal to L plus S, right? That's our formula for total angular momentum. And from that, we want to perform an inner product, right? J dot J, which is nothing but L dot plus S dotted with L plus S, right? So from this expression, you can see we have on the right hand side J square, and here what we have, L square from this dot product L into L, then we have L times S, so dot product between L and S, then we have S dot L. I'm writing them in the order they come first, but then you understand L dot S, S dot L the same because they commute with each other. So that's like twice L times S, right? So we have L square plus twice L dot S plus S square, right? So from here you can see that the L dot S, right? This operator is nothing but, you just bring all of the things on the left. So we have first J square, then we have this, say this is S square on the left hand side, then we have this L square, right? And then a factor of 2. So L dot S is nothing but half J square, S square, L square. And you will see why we are trying to express L dot S in terms of the squared operator, because you remember from the previous lectures that on the state we know what J square, what S square, what L square provide, but we don't know what L dot S, right? That's why it's good to write the operators L dot S in terms of, in a form where we can find out the expectation value, right? Now this L dot S, if you put in this expression, you can see the left hand side will become, there's a half, so it will become L square 3 by 2, then this expression plus 2S square, right? So let me now write it down. What is the left hand side? The operator part only, right? So on the left hand side, if you put all the operators, it will become 3 by 2 J square minus half L square plus half S square. Sorry, that should be half S square, right? And that's the right hand side. And can you see where I am putting all those values, right? So on the left hand side, we have this L square, L dot S, sorry, L square, 3LS and 2S square, right? So you will put the value of L dot S from this expression, and you can see there are some other factors, L squared, 2s squared. Just do the calculation. It's very simple, right? You will just do some addition and subtraction, and you will get this expression on the left hand side as an operator, right? And what's the good thing about this? Now if somebody tell you to find the expectation value of this operator, that's easy, right? Because this expectation value is nothing but separately you need to perform this expectation value, right? They're the same. So that's why we do this manipulation, so that every operator is now some squared, L squared, or J squared, because we know how to operate with these values. And if you remember, right, what's this expectation value from the previous lecture? It's J times 1 H square, right? What's this? That's like L plus 1 H square. And what is this? Half S plus 1 H square, right? So all this expectation value are known at this moment. So that's our left hand side. And do you remember what is the right hand side? Right hand side is nothing but G times this, right? So that's our left hand side, and on the right hand side we have J plus 1J H square. So all these H square terms get cancelled, and you can see we have G here, left hand side is this and right hand side is this. So finally we obtain the expression for our G factor, which is nothing but 3 by 2 J plus 1 plus half S plus 1 minus half L plus 1 divided by J plus 1, right? That's how the landed G factor. So in this expression you can see, if you know L, the quantum number of the orbital angular momentum, if you know S, the quantum number for the spin angular momentum, and if you know J, and J is nothing but L plus minus S, right? So if you know L, S and J, you know what is G, and that's the formula to calculate the G factor, the landed G factor, right? And that's an important quantity that will be useful during the derivation of our paramagnetic expression of an atom using the quantum mechanical consideration, right? So I hope I have gone through this derivation quite slowly. So have a look at this derivation and then try to understand different steps. And for this lecture, I think that's about it. And thanks for listening.